Okay, so let's see. Let's get started. So equivalence relations, again, you should have read plenty on this already and watch the videos and so on. I'm just going to skim through this really quick. We defined this last time. Let's see if you can remind me of this. What's an equivalence relation? Let's go for it.
It's a relation that reflects you symmetric and transitive.
Very good. So recall, and if A is a set, okay, then an equivalence relation on A is a relation, of course, that is, it has the three properties. It's reflexive, symmetric, and transitive. Okay, that's what an equivalence relation is. And you're going to see pretty soon why is it that we're interested in equivalence relations. But what was our main example for equivalence relation? That was an example. So suppose that A is a positive integers. What was an equivalence relation that we established in this? What was it? Which one do we do? Do we do mod 5 or mod 7? Let's see. We did mod 5. Okay, so let's use this one. So then A congruent to be mod 5. I'm using C++. You could use Z, but actually I'm gonna use Z because for the reflexivity, for the symmetry argument, we need the negative. So let me use Z here. So AC, and then let's put R to be, these are the order pairs A comma B, such that A is congruent to be mod 5. Now remember what this means. This means that they have the same remainder when divided by 5. Okay, that's what it means. And we saw that this is an equivalence relation. So this is an equivalence relation. I'm bringing this up because I'm going to use this for the next idea. So see previous notes. To see why this is an equivalence relation, we prove it. We proved that it was reflexive, it was symmetric, and it was transitive. Now, the reason why we care about equivalence relation is because there is a notion of an equivalence class. Okay, so definition. So let A be a set. Let A be a set, and R an equivalence relation on A, whatever that is, okay? An equivalence relation on A. Now, let little a be an element in A. So for each element in A, we can talk about the class or the equivalence class of the element A. And how do we define this? It's going to be a subset of A, and those are all the elements in A that are related to this guy, okay? So let A be in A, then its equivalence class and they talk about this in the video. Then its equivalence class is the following set. So this is the notation that I like to use for equivalence class. I think in the book, in the video, they use like with a bar or something like that. Okay, I don't like that one. So this is more commonly used. So then the equivalence class of A, of this element, is a set. And what is this? These are all elements in A. I'm going to call them B, such that A is related to B. Sometimes we have more than one relation going on a set. So typically, we like to put as a subscript here the relation that we're talking about, okay? So I'm just putting R here to say that this is the equivalence class of A using the relation R. When misunderstood what relation we're talking about, I'm not going to be writing this, okay? So I'm not going to be writing this every single time. but to avoid confusion, sometimes we like to put here the letters that we're using for the relation. Okay. So in other words, this is the collection of all elements in A that are related to this guy. Okay. These are, so this is the set of all elements in A that are related to little a. Okay, that's what that is. And obviously, you can see that clearly. So clearly, the equivalence class of A is a subset of the set A itself, right? Because every element here is an element in A. Okay, so it's clearly a subset. All right. So and the condition to be here in this set is to be anybody that's related to this guy. Okay. So for example, we have an equivalence relation above. Let's list what's the equivalence class of 3. So an example. In fact, list all equivalence classes. All the equivalent classes. Okay. So let me first I have to give you a theory. So from the above example, let me call that example 1. So from example 1, so list the elements in the equivalence class of 3. So what are the elements in the equivalence class of 3 in the above example? Remember, this relation needs to where two numbers are related, they have the same remainder when divided by 5. So what's going to be here on the equivalence class of 3? What is it? What are the elements here? Everybody who has remainder, the same remainder as 3 when divided by 5, right? What's the remainder of 3 when divided by 5? What is it? If you divide 3 by 5, what's the remainder? What does it mean to divide? Say that again?
It's 1 point something. The remainder.
Yeah, but here I'm talking about integer division. We're working on the integers. So what does it mean to divide? And 3 divided by 5 is 0 point something. That's 3 smaller than 5. So what does it mean to divide? Yes?
To break into parts of the same size.
Okay.
So the remainder will be 3.
Okay, so that would be 0 part with remainder 3. Remember, to divide two numbers, if you want to divide p divided by d, what this means that you want to write p as d times something plus something. This guy has a name. We call this the quotient or the result of the division. And this guy has a name. We call it the remainder. Because sometimes the division is not exact, right? Like for example, 2 goes into 8 4 times. So if you want to do 8 divided by 2, okay, then you can write it as 8 is going to be equal to 2 times 4 plus 0, right? Because it goes nicely 4 times into 8. The remainder is 0. But if you want to divide, I don't know, 6 divided by 4, well, 4 does not go even into 6 a number of times. It goes 1 time and then there are 2 remaining, right? There are 2 remaining. So that would be 4 times 1 plus 2. So 1 is the result of the quotient of the division and 2 is the remainder. Do you understand what I'm saying? That's what it means to divide, okay? All right, and of course there is a condition here for this to be unique, that the remainder, of course, is going to be anywhere between 0 and the divisor, the stuff that you're dividing by, strictly less than. For example, if you divide by 5, the possible remainders are 0, 1, 2, 3, and 4. That's it. Because if you have something larger than 4, let's say 6, okay, you can get another group of 5, and then you have 1 remainder. Do you understand this? So you will increment the quotient, and then the remainder you can always write it between 0 and 1 less than the number that you're dividing by. That's what it means to divide. so in this case, we want to figure out what's the equivalence class of 3, which means what are all the numbers that have the same remainder as 3 when divided by 5. That's our relation, right? So remember, the relation R here is, this is the set of all elements, I'm going to call them B, all integers B, such that B is congruent to 3 mod 5, right? And remember, in words, this means that B has the same remainder as 3 when divided by 5. And what's the remainder of 3 when divided by 5? 3, because notice that 3 is 0 times 5 plus 3, right? So it goes into 5 0 times, what is it? 5 goes into 3 0 times, and then leaving you a remainder of 3. Do you understand this? All right. So this is your remainder right here. So this is the same. So this is the collection of all elements B, such that B has remainder 3. Remainder 3. So now that we have spelled this out as much as we can, it should be very easy to list the elements here. Who can tell me what are they? So what are they?
8.
So we have 3. 8 is also there, right?
13.
What else is there?
13.
13. What else?
18.
18. What else? 23. Yes? Do you understand what's going on?
Yes.
You are only telling me positive stuff. Do we have any negative numbers in here?
-3. No.
The negative side is typically a little bit more. Now, look, there's a nice little pattern here. What pattern do you see here? What is it?
It's incrementing by 5.
By 5. So what would be the line before this one?
-2.
-2. And then?
-7.
-7, and so on. And indeed, if you think about it, how do we divide? Remember, this is what it means to divide, okay? You see up here. So if you want to divide -2 by 5, what is that equal to? Remember, that means you need to write it as 5 times something plus, 5 times Q plus R. So how can we fill this in? And then here, the condition here is that R has to be a number between 0 and 4. So now find the two numbers, Q and R. That's what division is, okay? Find the two numbers. What would they be? So what would they be?
-1 and 3.
So if you put a -1 here and you put a 3 here, that would be -5 plus 3. You understand this? And by the way, those are unique. You cannot find any other combination with this condition. This is the condition. R, that's what makes division unique, that the remainder has to be between 0 and 4, or between 0 and 1 less than the number that you divide. Okay? That way, that's or equal to. You should put a 5 here. We're dividing by 5. So here, it will be -1, and here we put a 3. So if you divide -2 by 5, the answer is -1 with remainder 3. Typically, we don't go around doing that kind of stuff, but this is what it is. This is integer division. Okay? That's what division means. All right, so it's finding those two numbers, Q and R. That's why we have this long division algorithm that allows you to figure this out for big numbers. Okay? Like if I tell you 2,137 divided by 5, that means that you have to do this. You want to write this as 5 times something plus something, and your job is to find Q and R. And how do you do this? You do your little long division thing. There's an algorithm that allows you to figure out this number and also this number. That's division. Okay. So you see, -2 also has remainder 3, so -2 has to be in this family. So let me go ahead and because I'm trying to make a list, so let me start here. So 3, 8, 13, 10, 18, 23, and so on. And then here we will have -2. Then what's the other one?
-7.
-7, and so on. Okay. So it's clear that if the padding is +5. Once you have 1, you want to go forward, do +5. You want to go backwards, do -5. Okay. And if instead of mod 5 is mod 7, you do +7, -7, and so on. You understand this? So all of these numbers, they are all related to 3, so they are all in the same equivalence class. It's 3. Do you understand this? Question. What's the equivalence class of 8? Is the same. Understand this? I mean, 8. If you think about it, you start at 8 + 5 - 5, you produce exactly the same set. Yes? So notice that this is the same as the equivalence class of 3. Also, another way to think about it is, okay, if 3 is related to 8, then 8 is related to 3 because our relation is symmetric, right? It's an equivalence relation, so it's symmetric in particular. And also, if 13 is related to 3, and let's see, 3 is related to 8, and 3 is related to 13, then you also get that 8 is going to be related to 13 by transitivity, because you can do this. So 3 is related to 13, and 3 is related to 8. Now here we can play the following game, because it's symmetric. This is the same thing as saying that 13 is related to 3. And now you can use your transitivity property and say 13 is related to 3, 3 is related to 8, therefore 13 is related to 8. You see that? So that means any number that's in here has to be down here in this class. That's what I just argued here. Okay? Anything that's related to 3 is also related to 8, therefore it has to be here. And the other way around, if something, because if something is related to 8, you can play the same game and get it here. So these two sets are exactly the same. Okay? I'm going to use that in a theorem pretty soon. So now, if I give you an element that's not in there, of course, the equivalence class is going to be completely different. For example, what's the equivalence class of 5? According to this relation, what's the equivalence class of 5? What's the remainder of 5 when divided by 5? 0. So this is a fancy way of saying multiples of 5, right? So 0, 5, 10, 15, 20, and so on. And then -5, -10, so on. Do you understand this? And notice that this is completely different from here. No elements in this set belongs to the one above. So these are disjoint. Okay? This is a theorem. Okay? So if A is related to B, then the class of A is the same as the class of B. If A is not related to B, then the two classes are disjoint. They have no common element whatsoever. Okay? So equivalence classes, they are used to group all the elements under the same relation. Let's say that you want to say that anybody that has the same remainder, you want to consider them to be the same number, then for us, all of these guys are the same number, for example. Because all we care about is remainder when divided by 5. So there will be no difference between a 0, 5, a 10, or a 15. Okay? All right. Okay, so anyways, that's the concept of an equivalence class. Do you understand this concept? Okay, so now that we have seen this, and we have seen that different elements are in, if two numbers have different remainder, then they have their own class. How many different equivalence classes are we going to have according to this relation? Wait, one more definition. Because of this, notice that these two guys represent the same set, right? Now, here I'm using 8. Here I'm using 3, but they are the same set. This is called a representative of the class, okay? So here, the number 3, this is an example of a representative of the class. Any element inside the equivalence class could be chosen as a representative because of this fact, because they will produce the same set anyways. So here in the definition, we say A is called a representative of the class. Okay? Okay, so then the question is, how many equivalence classes are we going to have? For example, here this is represented by 5, but what's a nicer number to use as a representative? 0, because it tells me the remainder. So how many different equivalence classes are we going to have? 5, because those are the 5 different remainders that you could have. 0, 1, 2, 3, and 4. Okay? And those are the representatives that we typically pick. You can pick others, but it's easier to pick the one that tells you the remainder. So notice that this is the same as the class of 0. So all equivalence classes of R are the class of 0, 1, 2, 3, and 4. Those are all the equivalence classes because they correspond to each of the remainders that you could have when divided by 5. This is for mod 5, the relation mod 5. So let's list them. So this is everybody that's multiple of 5, right? -5, -10, and so on. So this one right here is everybody that has what? Remainder 1. So what are they?
6.
So 1, and then 6, then 11, 16, and so on. How about here?
-4.
-4, good. Then -9, and so on. And here,
2, 7.
so it'll be 2, 7, 12, 17, etc. And then here, there's the -3, -8, and so on. There is a reason why I'm writing all this, okay? And then this one will be 3, then 8, 13, 18, etc. Then -2, -7, etc. And finally, this one is 4, 9, 13. No, 14, 14, 19, and so on. And then -1, -6, and so on. So those are all the equivalence classes. Now, question: what happens if I throw in all of these classes together? If I take the union of all of these classes, what do I get? We get all the integers. You see this? Well, what you're seeing here is called a partition of the integers. A partition of a set is just a collection of subsets that are disjoint. They have nothing in common, but when you put them all together, you get the whole thing. So what a partition means, you break stuff into pieces. That's why we call it a partition. This is a way of partitioning the integers, okay? According to their remainder when divided by 5. But now you can use remainder 6, remainder 7, remainder 10, whatever remainder you want. Do you understand this? Okay, so this is called a partition, and then one way to partition a set, another way to do so is using an equivalence relation. You want to partition a set, put an equivalence relation on it, and then the set of equivalence classes make a partition. Okay, as you can see in here. So let me give you the theorem that allows you to say all of these things. Let me say here, note that if I take the union of all of these guys, so the union of all of this, I produce all of the integers, okay? So, and they are all disjoints. Let me say here, these are disjoints, disjoint subsets. Remember, disjoint means that the intersection is empty, okay? So this is called a partition. This is an example of a partition of the integers, okay? So that's one way to create a partition. Impose an equivalence relation on it and then look at all possible equivalence classes, okay? And that's going to give you a partition of your set. Are there any questions on what an equivalence class is? Do you understand this? It's basically what tells you what do we consider these two elements, elements to be the same. For us here, anything that has remainder 0 belongs to the same family, so we put them in one little group. Everybody remainder 1, that's another family, we put in another group, okay? You can think of an equivalence class as a family. People that are related, so it's a family. All right, so let me give you the theorem. Now, this theorem is going to be in general, not necessarily with the mod relation. Okay. So let R be an equivalence relation on a set A. Then let A and B, let A, B be elements in A. Then the following are equivalent. This is commonly used in mathematics. Okay, TFAA. This means the following are equivalent. So I'm going to give you three statements, and the three statements, they mean exactly the same thing. So number one, A is related to B. Number two, the class of A equals the class of B. Number three, the class of A intersected with the class of B is not empty. So that means that any of these three statements, they mean exactly the same thing. They each imply each other. In other words, if you have an equivalence relation and you have two elements, and you know that A is related to B, that also means that they have the same class, which also means that the two classes intersect. They have at least one common element. And just by having one common element, everything is common, because then they will be equal. Okay? If they are equal, then of course these things are straightforward. This is the most interesting one, that if you have two equivalence classes and they intersect, that's it. If they have one common element, that means they have to be the same. They will merge together. Okay? So let's prove this. So for the proof, typically, there are many ways to prove equivalences of statements. Whenever we have something like this, we like to prove this in a triangular way, if possible. Okay? So the idea is we're going to prove that 1 implies 2. But instead of proving that 2 implies 1, we're going to prove that 2 implies 3. And then what we're going to do is we're going to close the circle by proving that 3 implies 1. And then by transitivity of implication, as you know, there's logical equivalence. For example, if you want to argue, oh, how is it that 2 implies 1? Well, you can say 2 implies 3, 3 implies 1, then 2 implies 1. Okay? So 1 implies 2, 2 implies 1, they are equivalent. So here we prove that 2 implies 3. How do you argue that 3 implies 2? Well, follow this diagram. 3 implies 1 and 1 implies 2, so 3 implies 2. Okay? So this way, instead of proving equivalence back and forth here, then back and forth here, and that would be 4 proof, right? Back and forth, it's 4 proof. If you do it like this, we only do 3 proof. Each arrow that you see here is 3 proof. Okay? So sometimes it's easier to prove the equivalence here and then to prove it with these two. But in this case, it's pretty easy that we can do it in the full circle. Okay, so this is the idea. Okay. All right. So the first arrow. So first, let's prove that 1 implies 2. How do we prove implications? Assume P, prove Q. So what's our P in this case? Statement number 1. What's statement number 1? That A is related to B. So suppose that A is related to B, right? Then our job is to show that the class of A is the same as the class of B, right? That's what we want to argue. Okay, now, so let me write down what we want. So I want to argue that class of A equals class of B. Remember, these are sets, so I need to show that the left side is a subset of the right side and vice versa. Yes? Okay, so how do you show that the class of A is a subset of class of B? So remember, this you prove in 2 steps. You need to prove this, and you also need to prove the other way around. So how do we prove? Let's prove the first part, okay? Let's prove this one. That class of A is a subset of the class of B. How do you do that? Take an element here, and for an arbitrary element in the class of A, we need to show that that element is also in the class of B, all right? Let's call it C. So I'm going to argue. So first, let's argue that the class of A is a subset of the class of B. So let's C be an element in the class of A. Well, let's call it X. All right, what does that mean? What does it mean to be in the class of A? So what are the elements in the class of A? What elements live in here? These are all the elements that are related to A, right? So then X is related to A. Yes? And notice that I could also say A is related to X. It doesn't matter because Since this is an equivalence relation, it's symmetric, so you can flip stuff if you want. Okay? All right, so let X be an element in the class of A, then that means that X is related to A. This is, that's the definition of equivalence class. All right, now we have that X is related to A, and we also know that A is related to B. That's our assumption. So X is related to A, and A is related to B by assumption. What can we deduce now? Why? By transitivity, right? So then X is related to B since R is transitive. Remember, being an equivalence relation means it's reflexive, it's symmetric, and transitive. So here we are enjoying the transitivity property since R is transitive. You okay with this? But now if X is related to B, what does that mean? It's an element in the class of B, right? So then X belongs to the class of B. So we started with an element in the class of A, and we showed that that element is in the class of B. So therefore, the class of A is a subset of the class of B. So anything that's related to A is also related to B. You okay with this? Now, how do we do the other way around? Should I really repeat? Basically, should I really repeat this? But not really. We can just say that similarly the other way around happens, because all you have to say is because A is related to B, just say that then B is related to A, and then you can play the same game. You switch A and B in this argument, and then you're gonna get that the class of B is a subset of the class of A. Okay? So number 2, similarly, just switch A and B in the above. Okay? And similarly, we get that the class of B is a subset of the class of A. So this establishes that the classes are equal. Okay? So that's how you can prove that 1 implies 2. So if A is related to B, that's all you need for the two classes to match, to have exactly the same elements. Are you okay with this? All right. So we proved 1 implies 2. Now we need to prove that 2 implies 3. Now this is easy. If the two classes are equal, does that mean that they have something in common? Yes, of course, right? So this requires no proof. So 2 implies 3. This is clear, since class of A equals class of B implies that the intersection is non-empty. And now this is because, for example, A belongs to the intersection, right? I mean, we know that this is not an empty set because we said there are at least 2 elements, A and B, in the set, right? And the element A is in the class of A because A is related to A by reflexivity, right? And because the classes are equal, then that same A is also in the class of B, right? Therefore, it is in the intersection. So the intersection is non-empty. Here you have to be very careful. You need to argue that they are empty, because if the set is the empty set, then everything is empty. We are not saying it. Okay? But why do we know that our set A is non-empty? Because I started by saying let A and B be 2 elements of capital A. So there are at least 2 elements here that we can speak of. Okay. All right. So 2 implies 3, and now finally that 3 implies 1. To close the circle, so 3 implies 1. So we're going to assume 3, which is that the intersection is non-empty. And then what do we want? We want to prove that then A must be related to B. Let's see. Who can tell me? How do we do this? So remember, we assume number 3, which is that the two classes have something in common. Okay? And then we want to prove number 1 that says that because of this, then A must be related to B. How do we do this? Yes.
You basically go to 2 and then to 1.
See, tell me.
Like, assuming that the unit
intersection.
intersection, right? And it's not empty. That means that they have to be the same, but like
How?
the equivalent class.
No, we haven't proved that. We only proved that 2 implies 3. We haven't proved that 3 implies 2. So be careful. If you want to, you can go ahead and prove that they are the same, and then, but we haven't proved that 3 implies 2.
To another equivalent class, right?
So we know that the equivalence class of A and the equivalence class of B, they have something in common. That's all we know right now.
And because they're equivalent classes, they have something in common. They're the same.
Why? That's what we need to prove. that's a theorem. That if they have something in common, then they are the same. This is part of the statement of the theorem that we need to prove. So we have proved that if they are the same, then they have something in common. That's what we proved. We proved 2 implies 3. We haven't proved that 3 implies 2. Now, I want to prove that 3 implies 1. I claim that that's easier. So how can we do that? Yes?
You can say that since the intersection is not empty, that they share at least one x.
Yes.
And that you can use the definition of the relation of equivalent class to prove that if x is related to A, then x is related to B.
Then what? Remember, our job is to show that A is related to B.
Yeah.
How do you get there? You are on the right track. If you just write it down, you are on the right track. Let's see. There is an element in the intersection. Let's call it X, right? So what does that mean? It's in the class of A, so X is related to A, right? It's also in the class of B because it's in the intersection, so you also have that X is related to B. How from here can you get that then A is related to B? Do you see how to get it? What would you like to have? What would you need to have to be able to say that A is related to B with this information? Okay, is A related to X? Why?
Because x is related to x.
That's not the same thing as A related to X.
Reflective.
Because it's no.
Relation.
Reflexive means everybody is related to itself.
No. Symmetry.
Symmetric. Remember, this is an equivalence relation. In particular, this is a symmetric relation. What does symmetric means? That you can flip stuff. Symmetric means that if X is related to A, then A is also related to X. Another relation is like this, like the division relation. Let's say 2 numbers are related if A divides B. For example, 4 divides 8, right? But 8 doesn't divide 4. So in that case, 4 is related to A, but A is not related to 4. So be careful. Okay, not every relation is symmetric. In this case, because this is an equivalence relation, it enjoys reflexivity, symmetry, and transitivity. Okay? Now here we want to get to A related to B. This is what we have. Well, that's easy. I know that this gives me A related to X by symmetry. Yes? And now you have A related to X, X related to B. What does that mean? A related to B by what? By transitivity. And we're done. Do you understand this?
That's what I just said.
Okay.
You just said what?
Okay. All right. So let's write it down. Okay. So we want, so assuming that the classes are non-empty, the intersection is non-empty, we want to show that A is related to B. Okay. So let X be an element in the intersection. Now, this is not an empty claim because we know the intersection is not empty. So there is something that's common to both. Okay. So then this means that X is in the class of A and X is in the class of B. And this is just definition of intersection, right? Now, I wrote it like this because I want to do 2 arrows. Now, from here, this means that X is related to A, right? And then from here, we get that X is related to B. What did I use? So here we use definition of equivalence class for both of these arrows. Okay, that's a justification. And here, what did I use to go from this line to this one? Definition of intersection. Yes? Okay, because it's in the intersection, it means that it's in both of them. Now, because it's here, it's related to A. Because it's here, it's related to B. Now, this is not exactly what I want. I want to prepare this a little bit more. Now, this means that A is related to X. Why? Why? By symmetry, because R is symmetric. Remember, it's an equivalence relation, so in particular, it's symmetric. since R is symmetric. So now I have A is related to X and X is related to B. So what can we conclude? So we have A is related to X and X is related to B. Then what do we say? Then A is related to B by transitivity. And that is exactly what we wanted. That's statement number one. Statement number one says, starting with a non-empty intersection to argue that A is related to B. That's what we just did. So we just proved that 3 implies 1, and we close the loop. So now you can get any implication you want by composing the ones that we already have, okay? If you want to get from 3 to 2, let's say you want to prove that 3 is equivalent to 2, well, we already proved that 2 implies 3. Now we proved that 3 implies 1 and 1 implies 2, so we also know that 3 implies 2 by composing those two, okay? And then you get your backward arrow here if you want, right? But this is a typical technique to do it in a triangular way, because this way we only did 3 proof. Otherwise, you have to do 4 proof. 1 and 2, 2 and 3. Okay? Or any other combination, but this is the most optimal one, doing 3 proof only. Okay, questions? Now, this theorem, the consequence of this theorem is that if 2 classes are disjoint, then they are, if 2 elements are not related, so if A is not related to B, then this has to fail, right? Meaning the classes has to be disjoint. That's what we saw here. That, for example, 0 and 1 are not related, so that means the elements in the class of 0 have nothing to do with the elements in the class of 1. Okay? So all of these classes are disjoint, so they make a partition. So a corollary of this theorem, and the set of all equivalence classes of a relation of an equivalence relation. Of an equivalence relation on A forms a partition. Okay? And the justification is exactly follows immediately from the above theorem. So that's one way of partitioning a set. Okay? Putting an equivalence relation on it and then look at the set of equivalence classes. Okay, are you okay with this? All right, so this is all I'm gonna say about equivalence relation. Any questions? All right.